SpaceX just flipped the script. Flight 12 didn't tweak the Starship formula, it shattered it. After 11 hard-fought prototype flights, suddenly the welds are flawless, the domes are enlarged, and the manufacturing floor signals a leap from wild experiment to factory precision. But why did even veteran SpaceX watchers miss signs of this radical transformation? And what does it mean for the future of reusability? The answer starts here. In less than 6 years, Starship's test campaign has become a story of relentless trial and error. Since 2019, SpaceX has launched 11 Starship flights, each one pushing the limits of what a fully reusable rocket could be. The early years were defined by Block 1 prototypes, brutal, welded together in the open air, sometimes flying, often failing. Out of those first attempts, only a handful ever left the pad intact. Explosions were routine. Stainless steel hulls crumpled under pressure, domes buckled, and test stands became scrapyards. Yet each wrecked prototype became a lesson, feeding a culture where failure was not a setback, but a catalyst. By 2024, Block 2 vehicles started rolling out. These ships looked sleeker, but the mindset was still experimental. Engineers swapped out forward flaps for thinner, lighter versions. Tank volumes grew by a quarter, pushing the limits of mass efficiency. Avionics and flight computers were overhauled, and electric thrust vectoring replaced hydraulics. The test record reflected that tension. 6 flights succeeded, and 5 failed. Flight 5 in October. 2024 became a milestone when Booster 12 and Ship 30 pulled off the first ever tower catch, a move that had seemed impossible just months before. The pace only accelerated. Over 5 more flights, SpaceX hammered away at the basics of reusability in space refueling, heat shield durability, and the brutal physics of long-duration coasting. Each flight was a rolling experiment, with ships patched, retrofitted, and sometimes rebuilt between launches. The manufacturing floor at Starbase churned out sections in a constant dance of welding, stacking, and rolling. Nothing stood still for long. The program's DNA was iteration, try, fail, fix, repeat. But beneath the chaos, a new rhythm began to emerge. Factory upgrades hinted at a shift from hand-built prototypes to something closer to an assembly line. Booster and ship numbers ticked upward, and the lines between test and production blurred. The first 11 flights were a high-wire act, each one a gamble. Now, with Flight 12, the evidence points to a program ready to leave the prototype era behind. The rules of the game are changing, not just for Starship, but for how rockets are built, tested, and flown. Production intent is no longer just an ambition at Starbase, it's visible in the metal. The hull of Booster 19 tells the story. First, gone are the jagged seams and hand-finished welds of early prototypes. Now, uniform fillet welds run the length of each barrel section, so consistent and smooth that they suggest robotic arms, not human hands. This kind of repeatable geometry isn't just for looks. Automated welding means stronger joints, fewer defects, and a pace that matches assembly line ambitions. The changes run deeper than the surface. The forward dome, once a point of weakness, has shifted upward. This subtle repositioning enlarges the liquid oxygen tank, squeezing more propellant into the same footprint. Analysts point out that the dome's new location is reinforced with layered steel plates, distributing the load from hot staging and boosting fatigue life under cryogenic stress. The methane transfer tube, now upsized and externally supported, adds another layer of robustness. During cryoproofing, a similar tube on Booster 18 prevented a full tip over after a catastrophic tank rupture, proof that these supports are not just theoretical. External bracing, once a patchwork of struts and gussets, has been pared back. The skin sits tighter against the tank, and cleaner panel edges hint at fewer rework steps. Each section arrives at the Gigabay already equipped with integrated hardware, reducing the need for on-site modifications. The result is a sleeker profile, but also a lighter one, with every kilogram saved feeding directly into payload capacity or reusability margin. Tooling tells its own story. The shift from rolling scaffolds and hand jigs to automated roller stands and production-grade fixtures is clear in factory footage. These are not just aids for workers, they are signals of a process designed for scale. Non-destructive testing methods, like ultrasonic and acoustic emission scans, now fit seamlessly into the build schedule, allowing for rapid retesting and faster turnaround between flights. This is how SpaceX is closing the gap between prototype chaos and operational cadence. The evidence is stamped into every weld, every dome, every joint. Flight 12 is built to fly, land, and fly again, with the factory itself as the quiet protagonist. Booster 19's return profile breaks all expectations. Instead of the familiar, symmetrical belly flop and grid fin ballet, the V3 Super Heavy cuts a side glide, an unorthodox move that caught even veteran SpaceX trackers off guard. As Booster 19 arcs back toward the Gulf, its asymmetrical Chinese and the now standard 3 grid fins work together to generate lift on a single lateral axis. The result is a controlled, banking glide, the booster riding its own aerodynamic edge rather than tumbling through the atmosphere. Telemetry overlays show a trajectory that bends more gently than any previous flight, with the return arc tracing a shallower, more fuel-efficient path. This is not just a new trick. It is a deliberate, production-grade maneuver designed into the hardware itself. The physics here are simple but powerful. By shifting to a side glide, Booster 19 exposes less surface area to the worst of re-entry heating. Instead of slamming into the thickening air, it skims, reducing thermal stress and spreading the load across reinforced Chinese. Observers noted the booster's descent rate slowed noticeably during the high-altitude phase, a direct benefit of the new profile. The grid fins are strategically placed, with one now absent, and they provide precise control, steering the massive rocket with fewer moving parts. This approach not only improves reusability by protecting key structures from repeated heat cycles, but also opens the door to rapid turnarounds between flights. Side-by-side overlays of Flight 11 and Flight 12 make the difference clear. Where earlier boosters dropped almost vertically, Booster 19 glides back with a pilot's touch. For the first time, the return looks less like a test and more like a routine. The never-seen tag flashes, but the evidence is there in the arc. A new kind of flight engineered for a future where rockets land, refuel, and launch again, all in a matter of days. Raptor 3 engines now power the heart of Starship's ambitions, and their presence on Booster 19 is more than a technical upgrade. It is a statement of intent. Each Raptor 3 weighs about 1,525 kilograms, nearly 7% lighter than its predecessor, yet delivers 22% more thrust. The numbers alone are striking, but it is the way these engines are built that sets them apart. Gone are the bulky external heat shields and tangled webs of fire suppression lines. Instead, internal cooling channels snake through the metal, drawing heat away from the nozzle and turbopumps. This design does not just look cleaner, it means fewer parts to check. less hardware to replace, and a faster path from landing to relaunch. On the manufacturing floor, welded joints have replaced dozens of bolted connections. Assemblies that once took days to fit together can now snap into place with robotic precision. The result is an engine that is easier to inspect, simpler to refurbish, and ready for the rapid turnaround SpaceX has promised. Analysts watching the static fire at Pad 2 noted how the engines roared to life with a clarity that spoke to both power and reliability. The test was supported by a new water deluge system, with a capacity far surpassing anything seen at Pad 1. Water blasted through the flame trench, absorbing heat and dampening vibration, protecting both the pad and the engines themselves. These upgrades are more than incremental. Raptor 3's streamlined design and Pad 2's deluge system are engineered for a future where launches happen not monthly, but weekly or even daily. This is the infrastructure of scale. Engines optimized for quick checks and fast swaps. Pads built to handle the relentless pace of production. For the first time, the hardware and the ground systems are aligned, each reinforcing the other, setting the stage for Starship's next leap toward operational readiness. Today, Starship's leap toward true reusability is not a distant promise. It is a visible shift on the launch pad and on the factory floor. As hardware transforms before our eyes, the countdown to off-world operations accelerates. The era of experimental rockets is closing. Now history gives way to actual interplanetary ambition. What's next?